Hello, welcome to my talk on the Enhanced Turbulence Models, Part 2. In this talk, we will introduce the popular and useful two-equation turbulence models in both practical applications and in the research community, including the Menter's SST model and the Algebraic Reynolds stress model enhanced two-equation turbulence models. Two-equation turbulence models are the most popular turbulence models in the practical applications, especially for the K-epsilon and K-omega models, due to their simplicity and their successful applications in many different flows. And the two-equation turbulence models are the least turbulence model for the complicated flows, according to Dublin in the reference. However, there are limitations for the two-equation turbulence models, and remedies have been proposed for improving the capacity of the turbulence models for different and wide applications, including some simple enhancement such as the low Reynolds number turbulence model introduced in the first part of the talk on enhanced turbulence model. The earlier K-epsilon model has strong free stream dependency as identified in the Menter's baseline model, and the problem in the construction of the eddy viscosity as seen in Menter's SST K-omega model. The limit of the Boussinesq's hypothesis, which may be inaccurate for the simple flat plate boundary layer or shear layer. Turbulence models with the algebraic Reynolds stress model enhancement via the nonlinear Reynolds stress expression. The talk includes the applications and the concluding remarks. I would first introduce the Menter's baseline model in this talk, which is often omitted in the introduction of the turbulence models. The reason for this introduction is because this baseline model serves today as the basis of the many turbulence models such as SST model, the omega equation-based Reynolds stress model, or even the DES detached eddy simulation models, which take advantages of the following turbulence models: the robust and accurate formulation of the Wilcox K-omega model in the near wall region, the advantage of the free stream independence of the K-epsilon model in the outer part of the boundary layer. So in formulating the Menter's baseline model, we have two different turbulence models: the original K-omega turbulence model and the transformed K-epsilon turbulence model. So the relation between the parameter epsilon and omega would be given as this. Here the coefficient beta star or C mu are both 0.09, as we have seen in the standard K-epsilon model. The transport equations for the turbulence kinetic energy K are same for both turbulence models. The only difference coefficient here sigma K1 and sigma K2. The transport equations for the frequency omega are given as this, respectively, for the original K-omega turbulence model and the transformed K-epsilon turbulence model. Here we can see the coefficient gamma 1, gamma 2, beta 1, beta 2, and sigma omega 1 and sigma omega 2 would be different. And the significant difference between the original K omega turbulence model and the transformed K epsilon turbulence model is the term here. This is a close diffusion term between the kinetic energy and the frequency omega. And this term is very important since the advanced K omega model has included the close diffusion term. So based on the two different turbulence models, the transport equation for the Menter's baseline K omega turbulence model would be given as this. The transport equation for the kinetic energy K and the transport equation for the frequency omega. And here we can see a blending function F1 is employed in this. Strictly speaking, the Menter's baseline K omega turbulence model is a zonal model uses the blending function F1. When F1 equals 1, the original K omega model is employed. And when F1 equals to 0, the transformed K epsilon model is used. And in between, the blending process is used. So the overall closure coefficients are calculated as phi, given in this formula. Here, F1 is the corresponding coefficient for the original K omega turbulence model, such as sigma K1, sigma omega 1, etc. And phi 2 is any constant in the transformed K epsilon model, representing sigma K2, sigma omega 2, and etc. And the baseline model, the coefficient is given by this blended coefficient phi. The eddy viscosity is calculated as this formula. This is the same as the eddy viscosity in the standard K omega turbulence model. For the Menter's baseline K omega turbulence model, we have two sets of the closure coefficients. For the original K omega turbulence model, phi 1 as this, and for the transformed turbulence model, phi 2 given as this. And the blending function is defined as F1 calculate as this. The argument is given in this formula. For different boundary layer, we see here the solid lines due to the different adverse pressure gradients. The corresponding blending function, F1, would be different. Here we can see that the Menter's baseline model starts to blending before half of the boundary layer thickness here, or even start at the quarter of the boundary layer thickness, the blue dashed line here. Menter furthered its development on the combined turbulence model, named as the SST model, short for shear stress transport model. The transport equations for the SST turbulence model is exactly same as those in the baseline model, but with slightly different closure coefficients. The overall closure coefficients calculated as phi given as this. Here the blending function is f2 and phi1, phi2 represent the closure coefficients for the original and the transformed turbulence models respectively. The significant difference between the baseline model and the SST model is the eddy viscosity formulation. Eddy viscosity is calculated as this formula. Here, if A1 times omega is larger than capital omega times F2, then the eddy viscosity is the same as that in the baseline model. So the closure coefficients and the relations for the Menter's SST K omega turbulence model are given. For this, set 1, phi 1 as this. If we compare the SST K omega turbulence model to the baseline model, we can see the coefficient for sigma K1 and sigma omega 1 are different. And the closure coefficient for the transformed K epsilon model are exactly the same as that used in the baseline model. So the blending function is defined as f2. If we compare to f1, we can see the difference of the formulation for f2 and f1. The argument for the blending function f2 is calculated in this formula. So if we draw out the boundary layer and the blending function, we have the drawing as this. And for different boundary layer, see the solid lines, we have the slightly different blending function f2. And we can see from this blending function, the Menter's SST K omega model starts to blend at nearly 3/4 of the boundary layer thickness. Then another difference for the Menter's SST K omega model is the blending function is not very sensitive to the different boundary layer. This is a very important feature for the Menter's SST K omega turbulence model. The example for comparing different turbulence models is the gyros flow, see in this picture, in which the horizontal circular cylinder is placed in the tunnel, and the experiment setup allows different adverse pressure gradients acting on the flow past the horizontal cylinder. This experiment has been widely used for calibrating the new turbulence models, and I referred to this experiment many times in my talk on turbulence models. The first example is the boundary layer profile on the horizontal cylinder at 5 different locations. The turbulence models include the Menter's SST, Menter's baseline, Wilcox K omega, and the Jones lambda K epsilon model. And from the comparison with the experiment data, we can see Menter's SST model predicts the boundary layer profile very accurately, best in all 5 locations, and the Jones lambda K epsilon model is the worst in all the cases. The second comparison is for the predictions of the turbulent shear stresses. Again, the comparison shows the Menter's SST model gives the best answers for most locations, although it might not be so good as that for the boundary layer prediction. In this slide, a discussion is made for the Boussinesq hypothesis. As we all know, in the turbulence models, such as 0, 1, 2, and some other turbulence models, the Boussinesq hypothesis is used for linking the Reynolds stress with the average velocity gradient at this. This hypothesis has always shortcomings, such as no historical effect on the Reynolds stress tensor. It cannot well represent the flow over the covered surface. The flow inducts with the second motions, and the flow in rotating frame, and also for some complicated 3D flows. For example, if we take the flat plate boundary layer or the simple shear layer, both are driven by capital U, Y. From the relevant references, we can see for the simple flat plate boundary layer, the normal Reynolds stress ratio for 3 different directions, 4 compared to 2 and 3. And in the simple shear layer, this 3 normal Reynolds stress are 1.07K to 0.23K and to 0.7K. So if we make an analysis to the Boussinesq formulation, we can see tau 11 given as this, tau 2 given as this, and tau 33, based on the assumption of the mean flow capital U is only depend on Y. So all these mean flow velocity gradients are 0. Therefore, we have all this Reynolds stress component at this. This will lead to the ratio of the normal Reynolds stresses. Those are equal. So if we compare this theoretical value to the experimental data, we can see the difference. Therefore, the Boussinesq hypothesis is very inaccurate even in such a simple turbulent flows. Basically, algebraic Reynolds stress models have been proposed for avoiding solving the 4 Reynolds stresses, so to reduce the computations in the modeling of the turbulent flows. However, in reality, the algebraic Reynolds stress model, including the traditional algebraic Reynolds stress model and the explicit algebraic Reynolds stress model, are not independent or self-contained. They can be applied only together with the 2-equation turbulence models, for which the turbulent kinetic energy K and the dissipation rate epsilon are available. As such, in the turbulent flow modeling, the computation would be slightly more than the conventional 2-equation models, but would be significantly less than the 4 Reynolds stress model, the 7-equation turbulence model. And this approach could remove some shortcomings of the Boussinesq hypothesis, such as the anisotropy of the Reynolds stresses. So as early as in 1970s, the problem has been recognized and the method have been developed for the problem. Roddy in 1972 and 1977 proposed the transport of Reynolds stresses would be proportional to that of the turbulent kinetic energy K, which means the anisotropy is constant along the streamlines, with the mathematical equation for the approximation given at this. Such an approximation would lead to an nonlinear algebraic equation for calculating the Reynolds stresses tau ij at this. Superficially, with the suitable approximations to the dissipation rate epsilon ij and the pressure strain correlation capital pi ij, this nonlinear equation can be used for solving the Reynolds stresses. However, to solve this nonlinear Reynolds stress tensor, we must specify the turbulence kinetic energy K and the turbulence dissipation rate epsilon. Therefore, this equation can be used for calculating the Reynolds stress component. Like many other explicit algebraic Reynolds stress model, which could remove some shortcomings of the simple Boussinesq hypothesis. In 1980, Wilcox and Lubison proposed a Reynolds stress tensor expressed in a form as this. Here, Sij is the strain rate tensor and capital omega ij is the vorticity tensor. And the coefficient 8/9 is used to ensure that normal Reynolds stresses would be correct in this form for the flat plate boundary layer. However, when we use this, we must have the variables k and mu t. This means this Reynolds stress tensor must be used combined with other turbulence model. And in 1992, Gadsky and Spazier proposed a Reynolds stress tensor as this formula, and the parameters Xi and eta are calculated as this. And again, we can see for calculating the Reynolds stress tensor, the parameter k and epsilon must be available. And in this expression, to ensure the fraction to be free of singularity, an approximation called theta approximation can be used as this. So in this slide, another explicit algebraic Reynolds stress model is introduced, which was proposed by Walling and Johansen in 2000. This model works on the Reynolds stress anisotropy tensor Aij defined as this. And in constructing the anisotropy tensor Aij, the long-dimensional strain rate S hat Ij and the capital omega hat Ij are defined as in this form. Here we can see the turbulence kinetic energy and the dissipation rate must be known. And the anisotropy tensor is given by this complicated formula. And the coefficient beta depends on the scalar invariant of S hat Ij and capital omega hat Ij. And also some other independent invariants are given in this form. In this slide, an application of the explicit algebraic Reynolds stress model enhanced the turbulence model to a high-lift airfoil, the relational high-lift program, and HLP. This airfoil is a 3-element airfoil, and the comparison is made for the angle of attack 20.18 degrees at the Mach number 0.197 and the Reynolds number 3.5 million. The pressure coefficient at the station 1 and station 2 are compared. Here the turbulence models include the new K-omega model with the explicit algebraic Reynolds stress model enhancement, the Menter's baseline K-omega model with the explicit algebraic Reynolds stress model enhancement, and the Menter's SST K-omega model. So from the comparison with the experimental data for the pressure coefficient, we can see all 3 turbulence models predicted the coefficients very well for this very complicated flow. So from this table, we can see 3 K-omega turbulence model with the enhancement of explicit algebraic Reynolds stress model. It can predict the lift very accurately with the error about 1% or even less. Here, for a comparison, the Wilcox K-omega model is used. Its prediction for the lift is slightly over 2%. And for the drag prediction, the Ramsey K-omega model with the explicit algebraic Reynolds stress model give the very accurate prediction. So in this example, we can see even with the enhancement of the explicit algebraic Reynolds stress models, it cannot guarantee a good prediction. And in this example, we can see, compared to the prediction of the lift, the drag prediction is much more complicated. According to Menter, turbulence modeling, especially the Reynolds models, would remain the optimum choice for many years to come, with the modeling of laminar turbulent transition in the focus. In the author's opinion, the most popular turbulence model in the industry applications would be the Menter's SST K-omega turbulence model, followed with the Sparnat-Omelas one-equation turbulence model. The latter is especially developed and tuned for aerodynamics application. Relatively, the K-omega model could provide a good feature for the laminar turbulent transition modeling, but they are yet too sensitive to the free stream parameters. Therefore, Menter combined the advantages of the K-epsilon and the K-omega models to formulate the baseline turbulence model, which can be used to serve as the basis of many turbulence models, such as the SST model, omega equation-based Reynolds stress model, or detached eddy simulation models, and provide a blending function or method in developing new turbulence models or zonal method. The explicit algebraic RSM are basically the nonlinear extension to the Boussinesq's hypothesis, which accounts for the effects of anisotropy and allows the inclusion of curvature and rotation effects. In application, the turbulence models enhanced with an explicit algebraic Reynolds stress model could significantly improve the prediction of the flow as the prediction of the multi-element NHLP airfoil.